Hello, this is first part of the chapter 6.1, and we'll talk about some geometric definitions for the vector space. And again, chapter 6 is all about geometry of vector space. We will talk about things and how they distribute the space, and we will talk about like multidimensional spaces and how to measure it. But before we start doing this interesting analysis, we need a basic definitions, and that's this first intro part is intended to do. Okay, one of the most important operation in this section is the inner product, a dot product, which is defined between the two vectors. So we basically take first component of vector u multiplied by the first component of vector v. Take the second component of vector u multiplied by the second component of vector v. Continue all the way until we reach component n, and then we add all these products together. And you probably notice that it's really remind you a lot of a linear combination. So basically, when we treat one of the vector as the weight for the linear combinations, that can be interpreted. Or you can think about multiplying the matrix of one row by matrix of one column, also works. Or you can think about multiplying two vectors, one of these is transposed. Anyway, any interpretation would work, but the formula is pretty straightforward, and I promise you would like it eventually. And this dot product has several important properties. For example, property A, the order of multiplication doesn't matter. You can easily switch the order of vectors. Then the transitive property, if we are applying dot product to the sum of the vector u and v, then we can distribute our vector w multiplied by the u first, multiplied by the v second, and then add them together. The property C is basically telling us that we can pull out constant. If one of our vectors, say u multiplied the constant C, we can pull it out of the dot product, or we can distribute this constant to the second vector, whichever would give you the same result, the same number. And that's very important thing to remember about the dot products. That's just a number. And if we are taking dot product of vector u to itself, this dot product always gonna be positive or equal 0. And if it's positive, that happens only if our vector u is equal 0. And you probably already realize that that's because when we take a dot product of u to itself, we will have the same component of vector u squared. And since we are dealing with R2 a vector space, our squared of any number would be always positive. And this kind of measure is actually very important, the dot product of itself. It's actually help us to measure the length of the given vector, or it's give us another way to measure length of the vector. We know that in the two-dimensional space, we can easily measure length, like for example, using Pythagorean theorem here. The length of the vector with a, b will be always equal the square root of component y squared, which is in this case b, plus component x squared, in this case a. So you can think about this length as an expansion of Pythagorean theorem on the n-dimensional space. We basically can measure the length of the vector even if we have a vector of thousands components. All we have to do, take each components of the vector, square it, add them together, and take a square root. And we call this measure either length or norm. So you will often use these two ideas interchangeably in this course. And when we define this length or norm of the vector, we can actually introduce the alternative definition for dot product. We can actually, if we have a dot product of vectors u and v, we actually get the same number, when we multiply length of vector u by length of vector v and by the cosine of angle between them. And in two-dimensional space, it's really nice to prove it. You can just start with a low cosine and with a vector u1, u2, and v2, v1, v2. It's in the textbook, and I strongly recommend you to go through this proof. It's really nice and neat. Okay, so now when we can measure vector, we can actually change the length of any vector to be just exactly 1. Because it's nice, because it's uniform, it makes us do a lot of interesting things. So we can just take, for example, we can take a vector v divided by its length, and we call this such vector u a unit vector, or we say we normalized vector v and got u. Let's just try to, and this offer a huge actually advantage, or like this normalization process when we are searching for the basis in our vector space. Because before, when we search a basis, any vector length would be a basis, so we basically choose whatever we feel like. But now we can introduce a little bit more rigor organization to our vector spaces and the basis. We can, for example, demand that every single basis vector should be a unit 1. And we will see later that it offers us a huge advantage. It's give us a unique basis instead of like random choice of, not random, but still a million of different possibilities. Okay, let's just try to normalize something. Let's take a vector space W, which is subspace of R2. And this vector space W is spanned by vector X. 2 over 3 and with components 2 over 3 and 1. Let's just find a unit vector z, which will be a basis, a unit basis for such a subspace W. Okay, we can just start with a definition of our basis in the subspace W. We know that it consists of, it's spanned by R2, so it's spanned by vector X in R2, which means that it can be any multiple of our vector X. So like any of non-zero vector, which is multiple of our vector X, would be a basis for this space. So let's choose one of the vector to work with. For example, I really do not like this 2 over 3 fraction. Let's just take our vector X multiplied by 3 and get the nice looking vector with components 2 and 3. So, and here is we have a little small sketch when we plot our vector Y. X coordinate is 2, Y coordinate is 3. So that's our vector, and it's rather long, significantly longer than 1. So we need to normalize it to bring it to its length to 1. It should be this vector z, which has a length of 1. Okay, so we can use definition of our normalization to make vector y shorter. Let's first find what's actually the length of vector y. So, and again, we just take the components of our vector y. First component 2, square it. Second component 3, square it. Get the length squared is equal to 13. So the actual length of our vector y will be square root of 13. Okay, so now if we want to get the unit basis vector z, we need to multiply our original vector y by this scaling factor, which is inverse of the length of our vector, which happens to be square root of 13. So we'll multiply our vector y by the scaling constant 1 over 13. And we can again use the properties of the vector to bring square root of 13 inside our vector and get the 2 component of our unit vector z. And this is how we find the unit basis vectors. So now I would like you to go to the end of the chapter 6.1 and try to practice normalize the vectors and reduce our basis vector to a unit size.